Hello, folks. I'm Fatih, CTO and the co-founder of Edge Delta. I started my career in 2005 at Microsoft. I'm quite old. Initial couple of years, I worked on making Outlook search folders faster. Then a couple more years at Microsoft, I spent my time on making link servers more reliable. Link servers then turned into Skype and a team now. And around 2013, I moved to Twitter and mainly worked on making Twitter more engaged, especially on the tweet anatomy. Then some more years, I worked on making cat videos to start playing faster. Basically, I did a bunch of media stack improvements to start videos playing faster. Since 2019, I'm working on making log management scale to petabytes level at Edge Delta. I'm very excited to be here and share my learnings along the way. Before I start, I want to talk about something unrelated, but very important. I'm originally from Turkey, and south part of Turkey is very famous with its delicious food and a rich culture and history. Unfortunately, there was an earthquake in that region recently. Many buildings collapsed. Many people died or injured, and many fighting harsh winter conditions currently. I would like to suggest a website, donate.turkishphilanthropytpfund.org, if you would like to donate, and for the people in need. Thank you. Going back to Edge Delta story, I want to talk about my learnings on shipping Daemonsets at scale, but I want to make sure that there's some terminologies are set for the audience. So I don't know how we can do the voting, but I don't know how many people are familiar with the Kubernetes and the Daemonsets. But let me reiterate, even for the people who knows about this. Kubernetes is essentially a glue between your applications and your resources. It helps you schedule your applications in the resources you have. Resources being in this scenario are your nodes, your hardware, and the collection of it is called cluster. And you can simply tell Kubernetes like how many of instances of your application that you need to run. It can help you to schedule it. You can declare behaviors of application in terms of its life cycle, how it should be deployed, like roll back or roll forward scenarios, or what permissions that it needs. And Kubernetes handles these kind of complexity for you based on your application's declaration. Your applications in these pictures are running as a pod. Pod, you can think it as like, in most cases, it's a single container, but it's another term on top of container because you can have multiple containers in the pod, depending on your applications. And there's a specific type of pod called Daemonset pod. And you only need that, oftentimes you need that when you want to have one-to-one affinity to the nodes. And in the cases where you develop products around security, network management, or observability, where you want to have visibility to both resources, like your nodes and the application, therefore you want to be everywhere in that cluster, and you declare yourself as a daemonset. Daemonsets usually access to your node level details. It can, talking with the Kubernetes API, it can collect your pod details and give customers insights about their environment. Why it is critical for us? As an observability product who runs log management in the petabyte scale, we run our data plane in the customer environment, in the customer's Kubernetes environment. Our backend is also on the Kubernetes environment. We call it our control plane, where you control these agents So basically, the data plane that we have, the main purpose of it is to collect, process, and route your data and generate insights from it and deliver to the destinations that you configure. It could be Datadog, Sumologic, or Splunk, or in many other integration points. So that's essentially why it is important for us to be the daemon set on the customer environment, because we run our data plane there. We initially in 2019, when we started, we are Golang agent, and most of our application logic exists on the agent side. We were initially running on Windows machines and EC2 machines. Then later on, we start seeing environments, more containerized environments, the Docker, ECS, and the Fargate. And roughly at the beginning of 2020, we start seeing customers on the Kubernetes environment, which gives us a tremendous benefits of detecting and understanding many things about the customer's environment. And we no longer need to ask customers where their application is, where their log files are, like those paths and everything. We can grab all this information from Kubernetes API, and with less configuration, we can give more turnkey features to the customer. And I want to share an interesting statistics from CNCF in 2021. 96% of the organizations either using or evaluating Kubernetes, they have some kind of a Kubernetes workload. So that made us that made our focus mainly be on the Kubernetes, especially for that reason, and seeing this adoption keeping up. Three main things that we learn along the way, and the three categories: we learn things about scale, we learn things about performance and maintainability. So I want to share these categories. Let's start with the scale one. The initial thing is, it sounds obvious, but so your applications on the Kubernetes environment runs a container. So the first thing you do is actually pull your images from a container repository. And it turns out that for making things easier for the customer, we are putting our containers in the public repository. You can potentially put it in a private repository. You can implement your own container repository. Since it's not our core business, we don't want to spend time on it, and we want to make deployments as seamless as possible, so we prefer public repositories. It turns out that some vendors have interesting rate limits on the containers, and one of the vendors we were using has like 100 pulls per 6 hours per IP address. And you can think that customer runs usually behind net, so therefore you're more likely to, this container repository, more likely to see each instances of their nodes as a single IP and hit easily these rate limits. We switch into GCR. They have very generous container repository rate limits. And just keep an eye on these rate limits. And usually when you're on call with the customer and going through like first deployment, dealing with rate limit issues is not a good impression. So next thing I want to share is trimming the containers. There was an interesting couple of months ago, actually January 25th, I saw this tweet. What is the fattest Docker image you have seen in the wild? You should check the responses to that tweet. I've seen personally 4 or 5 gigabytes of a container images. When you're not careful, your container images can be really oversized and really big. It has the impact on the network if you want to download this into 10,000, 100,000 machines. But other than that, it has actually security issues. You need to, whatever you ship to the customer, at the end of the day, regardless it's inside a container or outside of a container, you own these and you become responsible on the vulnerabilities, whatever you have in your container. So I highly recommend a multi-stage build in the Docker files. I shared one sample of it, and this is roughly like 40 lines of a Docker file. But initial first 30 lines over here, it's all about setting up the build environment for my container and making sure that all the dependencies got installed, and I do the compilation. And I make sure that I always start from scratch and just carry over what I need from the previous build layer into the shipped layer. This step is, I shared links at the end of the slides. I will put it on the chat too. So just make use of multi-stage builds in Docker file. Again, it has multiple benefits. It can trim down your container sizes from gigabytes to just your application. In our case, it's like 90 megabytes or something. And it allows you to have the better security posture too, because whatever you have in your container is a risk factor for your company. You can also trim things further. Not just multi-stage is a good way, but whatever the binary you put into container, you can even trim it further. This part is a language specific, but I'm pretty sure it's applicable for other languages too. In the Go, there's an LDL flags, and by just using -x and -s LDL flags, you can remove your debug symbols from your binary that you're shipping to customer. And it can, often cases, like could be 50% of your binary size. In our particular case, it trimmed down our agents from 125 megabytes to 90 megabytes. And there's an interesting thing too. Brad has a really cool tool called Shotism. Since today, I don't know where the name comes from. It's an interesting tool where you can analyze your Go binaries. You can give this tool, and it gives you a SQL interface to analyze your Go binary. You can ask questions like, which packages contributes most into this binary size? And you can figure out unused dependencies, not needed dependencies, and you can clean them from your binary. And you can even further reduce your binaries. It's not something that we are not doing it continuously, but once in a while, every 2 quarters, we check and see what are the things we have unused dependencies, and we remove the heavy ones. And there are some interesting tools which can help you to do that. This is an interesting one. So, okay, we are installed as a daemon set. We need to figure out the environment, and we need to talk to Kubernetes API server. We need to ask server about, hey, what are the pods installed there? What are their namespaces? Tell me all the details about the applications. And by default, Kubernetes API, you can get this information, get these states, but we were doing the polling mechanism. With some frequency, we call the Kubernetes API and get that information. But imagine doing this with 20, 30, 50,000 of machines at the same time asking this question to Kubernetes API server. You can overload the Kubernetes API, and that's actually, you don't want to do it for the customers, because Kubernetes API also powers your customers' DevOps team, and they manage their Kubernetes system with that dependency, the API. So you want to be as efficient as possible. And luckily, Kubernetes provide an informer API. So this is their streaming API, which has a really small footprint and less number of connections that you create against the Kubernetes API. I believe they specifically created this API for that purpose, and we have seen drastic reduction on the load that we created on the Kubernetes API, even in large scale. We could argue that you could do, like, between daemon sets, you could do some jittering. They can all poll this Kubernetes API at different times. But Kubernetes streaming server informer API is pretty sufficient, and it's pretty good. The next thing that we collect from the Kubernetes API is actually the Kubernetes events. Why it is critical for us, like why as an observability we want to collect the Kubernetes events. When we generate an anomaly or an issue or an insight for the customer, we want to provide as much as context as possible so that resolution times of the issues as quick as possible. Kubernetes events can tell you the picture from the infrastructure side, like did the deployment started, where the pods were restarting, or recently a configuration change. Those can be, most of the cases, the root cause of the issue. And we want to collect these events so that we can attach them into the findings that we had for the customer. The interesting thing is Kubernetes events are for not specific to the node or pod. You can collect it. It's a cluster based details. So it's about the cluster. You can consume all Kubernetes events from a single node. You don't have to have all your daemon sets to grab that information. Then it raises another question. Okay, how can we have these 10,000 of daemon sets installed, and I don't need all of them to collect these nodes, but which one should collect it? So for that, we use a leader election. We actually open source it. It's on github.com /leader election. Internally, it is using Kubernetes API, Lease API, and there's a sample flow of it. And with that, we can choose a leader daemon set, and only that leader daemon sets will deliver us the events. And we don't have to overload the Kubernetes API with grabbing these informations from multiple or duplicating that data. We could argue that we can also do this by installing another pod that we don't call it daemon set pod, or some other pod can collect this information. We specifically didn't want to go that route, mainly to simplify deployment. That's also an important aspect for reducing the frictions with the customer. Every extra step that you can eliminate and from your deployment and reduce your footprint, it's a more better experience for your customers. So it's already not an heavy, big size of a data which can be handled by your daemon sets, and picking the just one leader did the trick for us. And luckily, Kubernetes were providing a lease API for us to pick the leader. Feel free to use that open source project in any part of your application. The next thing is performance. For us, this data plane, our agents, you can think it like, okay, we are not a mobile company. We are a SaaS company which handles with low volume data. But you can almost think these agents like mobile applications. Like, you want to know, you might have multiple versions of it. They might have different kind of workloads on them. You want to know how your agents operate out in the wild, because they are not in your data center. They exist in the customer data center. And if or when the customer comes with a performance question or an issue, you want to be able to grab information about their environment and your agents without involving the customer, so that you can provide the help as quick as possible. What we relied on that is the profiling. Profiling, I don't know how many people are familiar with the profiling, but profilings are the most detailed, high context information, debug information that you can have about your application. There are multiple types of profiling. You could do like CPU profiling, heap profiling, allocation profiling, Go written in the Go case, Go written or the Trex mutex profiling. You can look into your application from different perspective and find out the benchmarks, find out the bottlenecks on your application. what we like the way that in general it works, for example, the CPU profiling, it takes the snapshot of your call stack in some frequency, in seconds. You can adjust that, the hertz, they call it hertz. Like if you set it like 3000 hertz, in 1 second, it will take 3000 snapshot of your call stacks. When you merge them, you can essentially see what are the most busy functions in your in the runtime of your application. And it doesn't require any extra SDK to be installed. Luckily, in the Go case, it was just built in with the application. What we did, interestingly, we didn't open source this part. We will open source it, is the self-profiling. So our agents has this profiling capability in it. So we can control it from outside and trigger CPU memory profiling on an agent and upload these profile information onto an S3 bucket on demand. And we can find out the bottlenecks in the particular agent and the particular workload. This screen that you're seeing right now is showing the pprof of a CPU profiling, I believe. And what we did on top of this is, even in the healthy conditions, we continuously collect profiling in some frequency, very low frequency. At the end of the day, this is a lot of data. But once you dump all this information into an S3 bucket, you can run some offline jobs to create an aggregated view by just not looking at from the one agent perspective. But if you have like millions of them, 100,000 of them, you can aggregate them and see like which parts of your code contributes most of the heap allocation, which parts of the code most busy with the CPU and all. This can give you an indication on what to improve next in your application. So performance is a long-term battle. You need to do it continuously, and any tools that you can have to give you insights about this is very useful. The third pillar is the maintainability. Again, in some environment, this could be automated or triggered on demand. We have an updater implementation. This is open source too. It is behind the SaaS backend. It runs as a cron job. It can control the versioning of your pods and your agents. Basically, it can update based on the responses from versioning service and the metadata service. That way you can keep the versions of your agents up to date. In the cases that customer configured for updating automatically. In the cases it's not automatic, you can notify the customers and have your customer success team to contact them to go through the updating flow. And this is purely an optional setting. But if you ever need an environment where you continuously need to keep a versioning of your agents up to date, it's under HDelta/updater. It's open source as well. Again, just a summary, key takeaways. Watch out for 429s, your rate limits. Keep your container slim, multi-stage, and check your binary sizes. Use streaming API whenever possible when you talk to Kubernetes APIs, and consider continuously profiling your agents to grab more insights about the bottlenecks on your application.